Welcome to the second lecture of measurements and instrumentation. Today we'll be looking at the topic errors in measurements. So errors is always there in the measurement. It's highly impossible to remove the errors while you are doing measurement. So the measurement is associated with some kind of error. So there is always some difference between the measured value and the true value, and the analysis that we are going to do, or the error analysis, deals with identifying, classifying and analyzing these different errors. So we'll be classifying the errors into different types and we'll analyze it, and also we'll also look at some of the methods to mitigate these errors. Okay, so these are the risks that are included in the current lecture. Now, error is the deviation of measured quantity from the true value. Okay, and this particular value is known as the absolute error. That is, AM is the measured value and AT is the true value. Okay, this is the actual value of error. So you will have some measured value and you will have a true value which is the expected value. So the difference gives you the absolute error. And the error can be positive or negative. That is, the measured value can be a larger value or a smaller value when compared to the true value. Now, correction factor is a value that is added to the measured quantity to obtain the true value. That you can understand. So once you add a correction factor, you will get the true value. So correction factor is always negative of the absolute error that you already obtained. So it also can be positive or negative. Correction factor will be positive when error is negative, and correction factor is negative when your error is positive. Now, static error or absolute error is defined as measured value minus the true value. Again, this is independent of time. Whenever you measure, you will have some error in the measurement. Such a kind of error is known as a static error. And relative static error is measured with respect to the true value. You have the error, and when you calculate it with respect to the true value, you will be getting the relative static error. And once you convert this relative static error into percentage, you will get percentage relative static error. And this percentage relative static error determines the quality of the instrument that you use. So we'll see how you can explain the quality of the instrument. See here, you have instrument A and instrument B. So instrument A is having a true value of 2 amperes and instrument B is having a true value of 1000 amperes. And the absolute error or the static error for A is 1 ampere and for B is 10 amperes. And the relative static error is defined as the measured value minus true value, that is the error, divided by the true value. So here already the error is given as 1 ampere. So 1 divided by 2 into 100 gives you 50%. So the relative static error is 50% in case of instrument A. In case of instrument B, relative static error is error divided by, or static error divided by the true value. That is, we'll be getting it as 1%. Okay, so you'll be getting the value as 1%. So this simply means that if you are going to measure some quantity with instrument B, you are expecting an error in the range of 1%. But if you are going to use instrument A to measure some quantity within the range 0 to 2 amperes, you are expecting a higher relative static error. So you can conclude that your B is better than A. Instrument B is better than instrument A. Now you have a capacitor whose value is being measured as 205.3 microfarad. So your measured value is 205.3 microfarad and the true value is given as 201.4 microfarad. Now you are asked to find out the relative static error. So how will you get the relative static error? So that is percentage relative static error is given by the error divided by the true value. So again the error is given by measured minus true, and you will get this is the here also you have into 100. Okay, so this is the calculation that you need to do, and once you calculate, ultimately you will get the value as 1.94 percentage. Okay, which is the relative static error or relative error in case of this measurement. So here you can see that the capacitor value is being measured and the true value is also given. So from that you can calculate the error in that particular measurement or relative error in that particular measurement. Now the next error is limiting error. This particular error is specified by the manufacturer, and it is with respect to the true value of the quantity that is being measured, and also gives the range of operation. Now it is also known as tolerance or uncertainty. Now for example, you have an instrument which is having a range of 0 to 10 amperes. So you are able to read maximum of 10 amperes, and percentage limiting error is given as 1%. Okay, so remember this percentage limiting error is with respect to the true value that is being measured, not with respect to the full scale reading. So here your full scale reading is 10 amperes, but this limiting error is with respect to the true value. Now for a true value of 2 amperes, that is you are measuring 2 amperes with this instrument, so the limiting error will be 1% of 2, that will be 0.02. That is, when you measure 2 amperes you will get 1%, you have 1% error, that is this limiting error. So 1% of 2 is 0.02, and your measurement is expected to be between 1.98 and 2.02. The same instrument, when you measure 5 amperes, 1% of 5 is plus or minus, that is plus or minus 0.505, and the measurement will be expected in the range 4.95 and 5.05. Similarly, if you are measuring 10 amperes, you are trying to measure the full scale value 10 amperes, so the limiting error will be 1% of 10, that is 0.01. Now 10 is the true value, and the measured value will be is expected to be between 9.9 and 10.1. 10.1 is not possible actually, but theoretically we can say it is between this value. So maximum value is 10, this is not possible, but theoretically you can say that it is between these two values. I think you understand what I am trying to say. Okay, so remember the limiting error is between. So the limiting error explains the error that is with respect to the true value. Okay, and with the change in the measurement, your error also changes. The range of measurement also changes. Here you can see that once you measure 2 ampere, you are having an error of 0.02. You are measuring 5 amperes, you are having a measure of 0.05, and when you measure 10 amperes, you have a range error of 0.1. Okay, so this is what the limiting error is. Now the next one is guaranteed accuracy error, GAE. Okay, again this is specified by the manufacturer, but this is with respect to the full scale reading. Okay, this particular error is with respect to the full scale reading, and it is a constant error. Whenever you make a measurement with this instrument, if you are specified with the guaranteed accuracy error, you will have same error for all the readings. That is, you are having the same instrument that you have already taken, 0 to 10 amperes. you have a percentage guaranteed accuracy error of plus or minus 1%. Okay, now 1% error is a guaranteed accuracy error. So it is with respect to full scale reading. So the guaranteed accuracy error, the absolute value of this will be 1% of the full scale reading, that is 10 amperes. It will be plus or minus 0.1. 1% of 10 is 0.1, plus or minus 0.1. Now when you measure 2 amperes, when you are measuring 2 amperes, your error will be again 0.1, and you are expecting a value or measured value in the range 1.9 to 2.1. Again, when you measure 5 amperes, again your error will be 0.1, because this is a fixed error or a constant error through for the instrument. So it will be 5 plus or minus 0.1, that is 4.9 to 5.1. And when you measure 10 amperes, it will be 10 plus or minus 0.1, so 9.9, and this 10.1 you can neglect. Okay, 9.9 plus or minus 0.1. So this plus or minus 0.1 is a fixed value. Why do you get this as a fixed value? Because you are calculating this value with respect to the full scale reading. This 10 is the full scale reading of the instrument. So remember, the guaranteed accuracy error is with respect to the full scale reading, and whenever you make any measurement with that particular instrument which is specified with the guaranteed accuracy error, you will get the same absolute value of this error throughout. Okay, 2 plus or minus 0.1, 5 plus or minus 0.1, 10 plus or minus 0.1. If you measure 9 amperes, you will be getting 9 plus or minus 0.1, 8.9 to 9.1. So that is the concept that you need to understand. Now, when you compare with guaranteed accuracy error and limiting error, okay, so you have both the values specified. So you are given guaranteed accuracy error for the instrument 0 to 10 ampere instrument with a 1% of guaranteed accuracy error. So the value of guaranteed accuracy error will be 0.01. So this we have already seen, because you are calculating this with respect to 10 ampere, which is the full scale value, 10 amperes. Now when you are measuring 2 amperes, true value is 2 amperes, you are having, or you are getting a reading in the range 1.9 to 2.1, that is 2 plus or minus 0.1. Okay, now what will be the limiting error? How will you calculate the limiting error? When you are measuring 2 amperes, you are getting the value of error as 0.1. Now what will be the limiting error? 2 into this limiting error gives you 0.1, that is 2 is the true value. Always you are calculating a limiting error with respect to the true value. So true value into the percentage limiting error gives you 0.1. 0.1 is the error that you already have, because this is error which is throughout or fixed throughout your measurement. So your limiting error will be plus or minus 5%, or you can otherwise explain this as 0.1 is this particular value is 5% of 2 amperes, 5% of this true value. Similarly, when you are trying to measure with 5 amperes, for a true value of 5 amperes, you will be getting the limiting error as 2%, or 0.1 ampere, which is a fixed error because it is a guaranteed accuracy error, is 2%. Say, can give plus or minus also, plus or minus 2% of 5 amperes. Again, this will be 1% of 10 amperes. Okay, so always your guaranteed accuracy error is a fixed value, and your limiting error will be changing with respect to the true value. Okay, so we'll take another example. So here we are asked to find out the limiting error in case of an instrument which is reading, or it is expected to read 83 volts. So the true value is 83, and you have an instrument range 0 to 150 volt, and you have percentage guaranteed accuracy error of 1%. So your guaranteed accuracy error will be 1% of the full scale reading, that is 150, that is 1 by 100 into 150, which will be giving 1.5 volt. So this is a guaranteed accuracy error that you are expecting. Now you are measuring 83 volts, or you are expected to get 83 volts. So when you measure 83 volts, you are having a error of 1.5 volts. So when you are measuring 83 volts, you are getting a error of 1.5. So what will be percentage limiting error? Your percentage limiting error will be 1.5 divided by 83 into 100. It is there, so it will be percentage will be 1.8 percentage, or we can say 1.5 volt is 1.8 percentage of 83 volt. So 1.5 volt is 1.8 percentage of 83 volt. So this is what you are expected to find out. So your percentage limiting error will be 1.8 percentage. So you are given 1% of guaranteed error. So guaranteed error is 1% simply means that with respect to the full scale reading you are having an error of 1.5 volt. So when you measure 83 volt, you are having a fixed error of 1.5 volt. So this 1.5 volt will be 1.8% of 83. So this is your percentage limiting error. So this is what you are asked to find out. Now you will get certain cases where you will be asked to find out combination of different quantities with limiting error. Okay, you will be given limiting error, and you will be asked to calculate different combinations. So say for example you have two resistors, R1 specified as 50 plus 6%, plus or minus 6% is the resistance, and R2 is 10 plus or minus 3% ohms is the second resistance value. So you have to find out R1 plus R2, R1 minus R2, R1 into R2, and R1 by R2. Now the thumb rule is that for addition and subtraction you have to add absolute error, and for multiplication and division you have to add the percentage error. So when you add R1 plus R2, it is simple. 50 plus 10 gives 60. But what about the percentage value, the error? You have to include that error also. So while including the error, while you are doing some calculations, for addition and subtraction you have to use the absolute error, and for multiplication and division you have to use the percentage error. So we'll see. Now R1 plus R2. So the magnitude is okay. True value, that is 50 plus 10. You will be getting 60. This is okay. What about the percentage error? So when you are adding, when you are adding two quantities with limiting error, you have to use the absolute value. So how will you get the absolute value? This is 6%. So what will be 6% of 50? That is 50 into 0.06 plus 3% of 10. 10 into 0.03. So that will be getting it as 3.3. So this is how will you calculate the absolute value of this error? If you are having 6% error, that simply means that 50 into 0.06 is the magnitude. So what is 50 into 0.06? So that will be 3. Okay, so this value will be 3, and 10 into 0.03 will be 0.3. So when you sum them together, you will have 3.3. Okay, so 60 plus or minus 3.3. Again, this 3.3 is the absolute value. When you convert it into percentage, it will be 5.5 percentage. How will you convert this 3.3 into 5.5 percentage? That is 3.3 divided by 60 into 100. So what is 3.3? What is the percentage of 3.3 with respect to 60? That is 5.5 percentage. So when you add them together, you have to follow this pattern. Again, you take the difference. You have to sum up the error. Error is being added up. The magnitudes are being subtracted. So 50 minus 10, that is 40, and the errors are getting added up, plus or minus 5%. So when you go for addition or subtraction, you have to add the errors, which is in absolute form. And when you go for multiplication and division, you have to simply add the percentage error. That is, when you multiply R1 and R2, 50 into 10 gives you 500. You can simply add the percentage errors, 6% and 3%, you will get 9%. Again, when you divide R1 and R2, okay, 50 by 10 gives 5. Okay, 5 plus or minus 9%. You are adding up the error. So when you divide and multiply, you add up the percentage errors directly. So that is easy. And when you go for addition and subtraction of quantities with limiting error, you have to use the absolute values. So you have to calculate the absolute values, find out sum them together, get the absolute value of the error, then convert it into the percentage value. Okay, so that's what you have to do. Now you have to find out the equivalent resistance of these two resistors when connected in parallel across a DC source. Okay, so the R equivalent is R1 R2 by R1 plus R2. Okay, and R1 R2 is already established here, so that is 500 plus or minus 9%. And what is R1 plus R2? That is 60 plus or minus 5.5%. So this we have already calculated. Now how will you find out this or simplify this? So that is 500 by 60. This you can directly do, plus or minus. When you divide these terms together or divide these terms, what you will get? 9% plus 5.5%. So you will be getting the values 8.33 plus or minus 14.5%. This much ohms. Okay. So when you are connecting two elements in parallel, two resistors in parallel with some error, your error is getting magnified. That you can see. So remember, when you multiply and divide, you can directly sum up the percentage errors. When you add the quantities together, you have to take the absolute error. Again, absolute error of 50 plus or minus 6% is 50 into 6 by 100, that is 3, and for this it is 10 into 3 by 100, that is 0.3. Okay, so that is how you simplify it. Now you have different types of errors that occur in during measurement. These are systematic errors, random errors, and gross errors. Again, systematic errors are classified into instrumental error, environmental error, and observational error. So we'll see this in detail. So systematic errors, the first one is instrumental error. So the instrumental error can be due to manufacturing defect, there can be aging issues, and it can be also due to improper calibration. You have not calibrated against a proper standard. So this can be eliminated by using a proper measuring device which is being properly calibrated against a standard. And if you are knowing about the error, and if you know the correction factors, you can apply those correction factors also in order to remove the instrumental error. You can entirely change the instrument and use a new one which is free of errors. The second one in systematic error is the environmental error. So there can be errors due to temperature variations, humidity, dust, vibrations. So again, the effects of magnetic and electrostatic field also has to be considered for certain measurements. So these errors can be fatal in critical measurements. So this also has to be eliminated. Now you can provide some arrangement to keep the environmental conditions as constant as possible. And you have certain instrument which is free from these effects. Say can provide electrostatic shielding or magnetic shielding you can provide. Okay, and you can use instrument which is having no temperature effects or with minimum temperature effects. So you can have zero temperature coefficient elements. So such things can be used. Again, the disturbances can be eliminated by some techniques, and again you can use some corrections or calibration to remove these errors or nullify these errors. The third one in the systematic error is the observational error. So observational error is generally termed as the parallax error. That is, you are not viewing your pointer in case of analog instruments directly above the pointer. So in such cases, in the first case you have no parallax error, but when you are looking from one side, this side, you are getting a lower reading compared to the true value, and when you are looking from this side, you are getting a higher reading when compared to the true value. True value is where your pointer stands, so you are reading this value. So this is known as parallax error. So this can be rectified or removed by using mirrored scales. So when you look from mirror above, you'll have a reflection on the mirror, reflection of the pointer on the mirror, and if you have no parallax error, the reflection cannot be seen because reflection will be exactly below the pointer, so that you cannot see this reflection. If you can see the reflection, that simply means that you are not looking directly above this particular meter. So such meters are available with mirrored scales. Again, digital instruments, when you think of this, observation error is completely eliminated because you are having digits, so you have no issue of parallax error. Next type of error is gross error. This is generally due to human negligence. You are taking a wrong reading, you are not applying some correction factors and all, you are taking a wrong reading, and after reading you are recording the data incorrectly. So such issues can happen while you are taking the reading, especially during your laboratory experience and all. You have a lot of human negligence coming. So such errors can be eliminated by carefully taking the reading, and again multiple readings can be taken. So we have seen already about repeatability, precision. Okay, so multiple readings can be taken to verify your reading. And the last one is random error, which doesn't have any particular reason for its occurrence. It is also known as residual error, and this can be different errors that doesn't fall into the already set categories. Now this can be eliminated using some statistical analysis of the readings that are being taken. Okay, so this will be dealt in detail in the next lecture. That is a statistical analysis of different instruments, meter readings. Thank you.